कृषि सांख्यिकी का संस्थान, इसमें शिक्षण और प्रशिक्षण होते नित नए अनुसंधान। इसमें विकसित पद्धतियों से होते हैं परीक्षणों व सर्वेक्षणों के नियोजन एवं अभिकल्पन, किए जाते हैं आंकड़ों के विश्लेषण, कंप्यूटिंग फोरकास्टिंग होते सही आकलन। इनसे ही है दुनिया में इसकी सच्ची पहचान। IASRI है कृषि सांख्यिकी का संस्थान। कृषि वैज्ञानिकों को परामर्श देते हैं, उपयुक्त सांख्यिकी विधियों से निष्कर्ष उचित निकलते हैं। सूचना विज्ञान ज्ञान संवर्धन में सहायता करते, इनसे बने प्रौद्योगिकियां एवं नीतियां उत्तम हो खुशहाल किसान। IASRI है कृषि सांख्यिकी का संस्थान।
Thank you. Anything we start with lighting of the lamp. Light blesses us, takes us from ignorance to knowledge. Light takes us from darkness to the path which we want to tread. Therefore, we begin with lighting of the lamp.
आरोग्यं धनसम्पदः, शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः। शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते, दीपज्योतिर्नमोऽस्तुते। शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः, शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः।
Thank you. Let me welcome Chair of the workshop, Professor Indranil Mukhopadhyay ji, Human Genetics Unit, Indian Statistical Institute, Kolkata, and Chairman for today's workshop. Welcome, Professor Indranil, to this workshop. I also welcome our three eminent speakers, Professor Mamnoor Rashid from Department of Mathematical Sciences, DePaul University, USA. Welcome, Professor Rashid. Professor George, I think he is yet to join, Vice Chair, Research, Department of Biostatistics, School of Public Health, University of Pittsburgh, US. We welcome him. Professor Gaurangdev Chattopadhyay, Head, Department of Statistics, University of Kolkata, India. Welcome, Professor Chattopadhyay ji, to this workshop. My teachers who have joined this workshop, senior statisticians, respected Vikasda, colleagues from statistics fraternity, students, ladies and gentlemen, both who are joined from India as well as US and other countries. At the outset, on behalf of ICR, Indian Agricultural Statistics Research Institute, and on my personal behalf, I extend a very warm welcome to each one of you for your online gracious presence in the workshop on statistical methods of data integration in agricultural sciences at ICR, Indian Agricultural Statistics Research Institute. We are basically an institute of Indian Council of Agricultural Research under Department of Agriculture, Research and Education, Ministry of Agriculture and Farmer Welfare, Government of India. We work with the mandate, research, education, and training in agricultural statistics, computer applications in agriculture and bioinformatics, and advisory, consultancy services, methodological support, computational solutions to National Agriculture Research and Education System, which encompasses 113 ICR institutes, 74 agricultural universities, and 731 Krishi Vigyan Kendras. And we also support National Agricultural Statistics System in the country. We are a premier institute of relevance in statistical sciences. When I say statistical sciences, which encompass three disciplines: statistics, computer application, and bioinformatics, and their judicious fusion in agricultural sciences for enriching quality agriculture research and informed policy decision making. We are in the 10th decade in the service of the nation. We started in 1930 as a small statistical section in then Imperial Council of Agriculture Research and imbibed the new technologies in our gambit, and now 93 years in agricultural statistics. In 1965, the first computing facility of ICR, IBM 1620, as a data processing system was installed at this institute. Therefore, 58 years in computer application. And 2010, we established National Agricultural Bioinformatics Grade. Therefore, 13 years in agricultural bioinformatics. We are catering to the needs of National Agriculture Research and Education System, National Agricultural Statistics System, and e-governance activities of Indian Council of Agriculture Research. And simultaneously, we have to prove to our peers on basic research in statistical sciences. This is our brief about the institute. Now, let me introduce our chair for the today's workshop, Professor Indranil Mukhopadhyay. He is professor at Human Resource Genetics Unit, Indian Statistical Institute, Kolkata, since 2020. He had been associate professor during 2008 to 20. He obtained his PhD in time series analysis under the guidance of Professor Adhir K. Basu from Calcutta University. Postdoctoral fellowship, University of Pittsburgh, US. His research areas include statistics and probability, gene and gene environment interactions in genetic association studies, data integration of several genetic data sets, mathematical statistics. Some of his important research papers include a data-driven approach to COVID-19, resources, policies, and best practices, critically community size for COVID-19, a model-based approach to provide a rationale behind lockdown, determination of critical community size from an HIV/AIDS model on a novel statistical method for integrating multi-omics data, an integrative approach for particularly missing multi-omics data with an application to tuberous sclerosis. Welcome, Professor Indranil. I can hand over the platform to you for further deliberations, or if you wish that I should also introduce the eminent speakers, I can do that on your behalf. Professor Indranil?
Yeah, you can introduce the speakers then. Yeah, you can introduce, no problem.
Yeah, we
The
have
first speaker you can
three
introduce.
eminent
Dr.
speakers.
Mamnoor
Professor
Rashid.
Mamnoor Rashid. He is from the Department of Mathematical Sciences, DePauw University, Indiana, US. Prior to joining DePauw, Professor Rashid served as a faculty member at Indiana University, Purdue University in Indianapolis, and where Vikas Das says that he met Professor Mamnoor, and since then they are in touch. Held the role of director at Statistics Consulting Center there. He has earned his PhD in statistics from Bowling Green State University in 2008, and subsequently taught at Ohio Northern University for 2 years. His research interests encompass statistical computing, data visualization, data analysis, and application of statistics to public health and population studies. With his collaborators, Professor Rashid has published in various journals and developed R&R studio packages on Crate. Welcome, Professor Rashid. Professor George is the Vice Chair, Research Department of Biostatistics, School of Public Health, University of Pittsburgh. He has secondary appointments in human genetics and computational systems biology. He received his BS in 1997, MS in 1999 in mathematics from National Taiwan University under Dr. Huang Chen, and SCD 2003 in biostatistics from Harvard School of Public Health. He joined Pittsburgh since 2003 and leads a research group in bioinformatics and statistical learning. His research interests focus on statistical modeling and applications for omics and bioinformatic problems to improve precision medicine and human health. His research group has published large number of research papers, both towards a methodological as well as collaborative papers, and they have co-invention of 5 patents. He has number of awards to his credit, which include American Statistician Association Fellow, Statistician of the Year, and Provost Award for Excellence in PhD Mentoring, University of Pittsburgh. He has collaboration with biological and clinical labs, plays an important role where most of his projects and methodological ideas come from. Welcome, Professor George. We welcome Professor Gaurangdev Chattopadhyay, Head Department of Statistics, University of Calcutta. He is serving as faculty at University of Calcutta since 1995, Professor of Department since 2012. He had obtained his PhD in statistics from University of Calcutta in 1994 on the work related to foundations of statistical inference, and which has to be his main interest of the research. He is coordinating editor of Calcutta Statistical Association Bulletin since 2013, secretary of Calcutta Statistical Association during 2007 and 10. Being an excellent teacher, he has taught many courses, including real analysis, complex analysis, measure theory and probability, large sample theory, multivariate analysis, sequential analysis, parametric and non-parametric inference, Bayesian inference, and sample surveys. His research areas includes mainly statistical inference, both parametric and non-parametric, and to be specific, multiple testing, which is one of the most ubiquitous inferential tools used in statistical investigation arising in modern scientific research. And for today, he had chosen a topic similar to on the multiple testing. During his long career, he published many papers in reputed international journals. Apart from these activities, Professor Chattopadhyay is actively involved in popularizing statistics and delivered talks on different topics in colleges, universities, institutes, and various workshops on interdisciplinary research. Professor Gaurangdev, we welcome to the institute and to this workshop. I think now I hand over to Professor Indranil for the taking the workshop forward. Thank you very much.
Yeah, thank you, Professor Prasad. So without much delay, since you have already introduced all the speakers really nicely, so I invite Dr. Mamunur Rashid. We are all waiting to hear from you. Dr. Rashid, please join. You can share your screen and you start your talk. I think you can take around 55 minutes, 50 to 55 minutes, and then we leave a few minutes for questions.
Good morning, everyone. Thank you very much, Professors Prasad and Mukhopadhyay, for nice introductions. My name is Mamunur Rashid, as you heard. So I'm a professor here at DePaul University in Indiana. And thank you for inviting me to deliver a talk in this workshop on statistical techniques of data integration, focusing on agricultural sciences. Well, before my presentation, I would like to thank and express my gratitude to Professor Bikash Sinha, who has joined us today. Actually, he has introduced me some of the ideas of data integration technique. If I remember correctly, Professor Sinha visited IUPUI, which is a Indianapolis campus of Indiana University, I think around 2015, as a visiting scholar. So at that time, he gave a series of talks, and one of the talk was data integration techniques. Actually, I was motivated with his talk, and then later we collaborated and published a paper in this area. Thank you once again, Professor Sinha. for introducing this topic. So my title for today's talk is Data Integration Technique in Agricultural Sciences. So this is the abstract probably shared with the audiences. So the main purpose for today's talk is to get familiar with some of the data integration technique. Probably I'm going to share with one of the technique that is used in a published paper, which is basically ranking of various DNA extraction methods when extracting DNA from soil samples. So the contents of my talk is I'm begin with a few motivational examples and method overview. That method basically applied in that article, and then we'll provide that example illustrations from that article, and then I'll share with some calculation demonstration that I have used based on the dataset that published in that article using Excel and also using RStudio. So here are some motivational example of why the data integration technique plays an important role. So think about, suppose you want to purchase a mobile phone. So there are many brands out there. So which brand will you purchase? So there are lots of criteria that we need to take into consideration. For example, here some of the criteria could be price, it could be storage capacity, it could be camera, how many megapixels, and then how attractive that phone is, or even there are some more criteria. If there are more criteria like that, then it's difficult to choose or figure out which mobile phone basically serve the purpose. If you look at another example, for example, here, like which car model will you buy? So there are some car models on the left side, like Toyota Camry and so on. And then we'll be looking into some criteria before we purchase the car. For example, the price of the car, fuel economy, how reliable the car is, and then style and so on. So there could be other criteria as well. So if considering all those criteria, if you want to figure out which car model we're going to purchase, then we can make a decision that car serve my purpose consideration by considering all those criteria. There could be another example like this, say a graduate after graduations applied for many jobs, got 4 or 5 job offers. Now, which job offer will that graduate will accept? So of course, there are considerations like salary, location from the current place, think about like health insurance cost, retirement plan, and so on. So considering all those things, the candidate or graduate can choose what the job is best fit for that graduates. So think about each of these example I provided here. Say, for example, the first one. So considering this criteria, if you want to figure out like which mobile phone will someone purchase, so the decision is getting harder. Like if we have more criteria to choose from, then the decision really, the decision of purchasing one of the phone is harder. So in this situation, the data integration technique plays a very important role. So what is data integration? Data integration means basically we integrate data to gain insights and make informed decisions. Basically, the aim of data integration is to combine and integrate various data sources and criteria for the purpose of decision making. So nowadays, data integration technique applied businesses, various organizations to make such informed decisions. One of the data integration method to compare, rank, and order several alternatives is based on the notion of multiple criteria decision-making methods. So basically, multiple criteria decision making has been recognized as an efficient statistical method to combine component indices arises from various sources into a single overall meaningful index. Therefore, ranking and comparing are feasible. So this MCDM method basically advocated by Wang and Yuan in their 1981 landmark book called Multiple Attribute Decision Making Method and Application, a State-of-the-Art Survey. So in this book, they discussed various decision-making model, and then they discussed some of the method they have developed over the course. So when I was looking into searching the literature, there are so many methods researchers have been developed since then. Like there are listed some of the methods, this slide, and then next slide. So people have done so many works on multiple criteria decision-making model. So my purpose today to share with one of the technique that the article I chose, they have used that method, and I have used that method previously in my other paper. So this method is called technique for the order of prioritization by similar to ideal solution. In other words, we call that TOPSIS. Okay. So that's the technique I'm going to share with you, give you some brief mathematical overview and also some computational algorithm to understand. So what is TOPSIS? As I said, this is the technique for order preference by similarity to ideal solution. So this method is developed by Wang and Yuan. So this approach is basically based on the intuitive principle that the best alternative should have the shortest distance from the ideal alternative and the furthest distance from the negative ideal alternative. So the main feasibility of this method has many advantages, such as its simplicity, rationality, comprehensibility, good computational efficiency, and ability to measure the relative performance for each alternative in a simple mathematical form. Basically, the TOPSIS method is like it carries easiness compared to the other multiple criteria decision-making model. Is mainly this TOPSIS method maximize the benefit and minimize the harm, just like wise business solutions. So just sharing with you some mathematical ideas behind this method, like here are some notations. So AI, it takes value 1 to m that represents the alternatives, and then CJ, J takes value 1 to n that represent the decision criteria, and then WJ, those are the criteria weights. It requires some importance to assign those weights to this criteria. And then XIJ, basically the values of the ith alternative and jth criteria. So in a TOPSIS method, based on these notations, we can define the decision matrix that requires for the TOPSIS method. So based on the previous notation, these are the alternatives on the first column, and then top row, these are the criteria. And then each criteria needs to assign certain weights. And then the elements, these are for the ith alternative and jth objects. So these are the elements in the decision matrix. So before we proceed for the TOPSIS algorithm, it requires some hypotheses to keep in consideration. The first one is each criteria in the decision matrix takes either monotonically increasing or decreasing values. For example, here, so we have n criteria. All criteria needs to be the same order, either increasing or decreasing order. The next hypothesis is if any of these criteria are non-numerical, then we need to convert it to a in a certain if there is a categorical nature, then we need to provide those numerical values. We need to certain scale it. And then third hypothesis is this set of criteria, it requires certain weights that we need to assign. Okay, so to get this criteria, the question is, are those criteria are equally important? Then we can choose the equal weight for each of these criteria. So in reality, probably not. So it requires some based on the relative importance. So think about the cell phone, mobile phone examples. So there are different criteria. Not all criteria are equally important. So we need to assign certain weight based on that relative importance. So now how do we assign those weights? Well, it could require some expert knowledge. So occasionally it's not possible. So we need to figure out certain way to assign those weights. So there is a data-driven technique that we can use. That one is called the entropy weight. There are many weights people have developed over the course. And these are the sum of the weights that you can integrate with the TOPSIS method. So our focus aligning with this article, we're gonna use the entropy weights. So basically, among different criteria weight assigned in the TOPSIS method, entropy is among the very few techniques that are independent of the decision maker's subjective judgments. In this entropy method, the criteria weights are calculated based on the actual data that we have provided in the decision matrix. So here is the algorithm, computational algorithm for the entropy method, that also called the Shannon entropy. So first, we need to convert our decision matrix into normalized mode. Then basically, we need to calculate the entropy degrees of diversity. And then based on that, using these mathematical tools, we calculate EJ, which is the entropy, DJ, degree of diversity. And then we're gonna use this to calculate the WJ, which is the weight. So W1, W2, Wn, those are the weights corresponding to each criteria, and then summation of Wj that turns out to be 1. So this weight needs to be integrated to the TOPSIS method. So here is the algorithm for the TOPSIS method. So we have a decision matrix. The first, there are 5 steps we need to go through in the computational purposes. The first step is based on the decision matrix, we calculate the normalized decision matrix, which is the each value we have in the decision matrix divided by sum of scores and then take the square root of that. So we call the Rij. And then next step, we calculate the weighted normalized decision matrix. We call the V, so that each element in V is basically Rij multiplied by the weight we calculated using the entropy method earlier. And then we need to calculate ideal positive and ideal negative. This is very important based on like the criteria we have. As we mentioned, that one of the hypotheses, all criteria needs to be the same order. So in a data set, when you'll be dealing with, not all criteria may not be same order. So for example, one situation could be higher is better, but one of the criteria may be given lower is better. So that means we need to reverse it to make in the same order that higher is better. So in this situation, so this Vj is the ideal positive. So that means we need to keep in considerations based on the maximum and minimum will based on this alternatives we have, we need to identify the ideal positive, and similarly we need to find the ideal negative. So when I will share with you the example, then this mathematical concept here will be easier. And then next we need to calculate the Euclidean distance to find one is called the D plus, that we calculate the distance from the ideal positive, which is the each element of Vij, and then we subtract that one, which is basically L2 norm of the Euclidean. And then second one is we calculate the negative ideal based on we calculated the Vj, which is the ideal negative. So once we calculate di plus and di minus, these two distances, we based on this, we calculate a composite index. So which is di minus and then divided by di plus and di minus, which this composite index takes values between 0 and 1. And these composite indices are used for our final ranking. The rule is maximum to minimum for ranks, that which gives us 1 to the highest alternatives we have. Okay, so these are the some basic mathematical algorithm behind the Topsis method. So we're gonna implement these mathematical tools with an example that was published in this article of 5 authors. That article is published in American Journal of Molecular Biology. So the title of this article is DNA Extraction Method Selection for Agricultural Soil Using Topsis Multiple Criteria Decision-Making Model. So this is the front page of the article. The authors are from 2 universities, University of British Columbia and then McGill University in Canada. So so this is the open source. Anyone can access to that article just searching the title of it. So the main purpose of this article was to select the best extraction method, which is cost-effective, capable of rapid processing of multiple samples, and able to high-quality DNA suitable for PCR studies. Well, I'm not a subject matter expert, so basically I'm going to share with you the Topsis method integrating to fulfill these objectives. So in this article, they discussed actually the 10 DNA extraction methods. Those are the 10 methods. So each of these has like convention and alternative methods like ultra clean, power, soil. So these 10 extraction methods are to be compared under 7 performance criteria. So the criteria are here, the C1 to C7. These are the name of the criteria, for example, yield of extractions. So here are the criteria values. So it's saying that the first 3 are higher, the better, and then bottom 4 are the lower, the better. So remember, one of the hypotheses in the Topsis method, all of them needs to be monotonically increasing or decreasing. So when you apply the Topsis method, we need to keep in mind and then make this order accordingly. So the data set is given in this table according to this structure. Basically, based on that, we can build our decision matrix for the Topsis method. So these are the 10 attributes or alternatives that we want to rank based on these 7 criteria. So it does match exactly the way we discussed the decision matrix we have in our Topsis method. So this is the decision matrix. So if you compare with the alternatives, so we have basically M equals 10, and then criteria we have 7 of them. So all we need to do is to calculate the weights based on the data we have given based on this study. So in this study, basically what they have done is for each of these, they conducted this study for soil in 3 different cases. One is the soil, one is the soil manure, and other one is the soil manure biochar. So these 3 cases they replicated 5 times, and based on that they created or they fill out this table. So we'll not do all those 3. So I'm going to share with only one scenario, which is the soil. So based on the soil, so we have we get our decision matrix. We have basically bottom 2 attributes or alternative, they have some missing entries. So this article, they remove these 2 alternatives. The based on these 8 alternatives and 7 criteria, they rank it. So we have a data set like this. So we are not using any expertise judgment to find the weights of each decision criteria. So we are basically doing data-driven decision criteria, the weights for criteria using entropy method. So using the entropy methods, so we calculated EJ, degree of diversity, and these are the weights. So when you add all those weights, it turns out to be 1. So not all those criteria are equally weighted. Some has more weight. Some of them are not contributing any of them, for example, C2. So aligning with the articles, we are keeping all those criteria and then rank those 8 attributes or alternative, 8 alternatives we have. So based on the algorithm or following the computational mathematical steps of the TOPSIS method, we completed like table 4 that provides us a normalized decision matrix. And then we calculated the weighted normalized decision matrix. And then we calculated positive ideal or ideal positive, and then negative ideal based on the criteria. Like if you have the alternative, here is the 8 alternatives. So V plus is, which is the maximum among all those 8 alternatives. So this is the ideal, and then this one is the negative ideal, the smallest one. So to make on the same order, so this 4 was the lower is the better, so this 3 is the higher is the better. So we make into the same order. So that means we consider lower is the better among all those 8 alternatives, so that they are all in the same order. And then we calculate the DI plus and DI minus using the Euclidean distances. Based on that, we calculate the composite index. And then this column is used to rank all those alternatives. It turns out to be the power soil DNA isolation kit, which is this one, power soil DNA isolation kit, as the optimum method for obtaining total bacterial DNA from soil. So one thing I need to mention that this article has some calculation mistakes that Professor Sinha and I noticed, and based on that, actually, we considered some other different weights, and then we basically published an article. So this one is the bottom one, is the data integration techniques in agricultural sciences. That's the first paper we published considering this, applying this TOPSIS method. And then this is the recent one I published with my students and other collaborators. Well, thank you. This is my talk based on the TOPSIS method. And then I'm going to share with you just briefly some of the computational tools that I used. Like I used the Excel to integrate all those mathematical or computational steps. So first up is the entropy weight, and then based on that we got the weight for each of these criteria, and then again summation of all those weight must be 1, and then we integrate this weight in the TOPSIS method to calculate So these are the steps: normalized decision matrix, weighted normalized decision matrix, and then finally we rank those alternative. Considering that, again, we come up with this matches with exactly the author found in the article, but some other of the ranks do not match due to some calculation matrix in the mistake in the original paper. So this is the, like, if you have a small data set, this is quite easily doable using Excel, just following this algorithm. But if some, I know that nowadays many of us use R or R Studio. So using R also, we can calculate this ranking. So I did in two different ways. One is the manually just following the algorithm. So for example, so this is the data set. We have in terms of a matrix. So this part data set as a matrix, and then we calculate the entropy following that algorithm. And then, so if you want to do the manual calculation of the Topsys algorithm, just write down few quotes, and then it provides us the ranking of this. So if I run this, so it gives us exactly the ranking we have calculated in the Excel file. So that gives us, this one is the highest ranking, which was the power soil. So also, those of you are using R every day, there is a package inbuilt. I mean, not the inbuilt, you need to upload a package. It's called the Topsys. So I also ran this one that provides the same result as well. So this is called the Topsys package. So after installing the package, incorporating the weight using the Topsys or any other method we use for the weight, and then we just run the Topsys function to do that. But there is the I, that's the part we need to keep in mind, like all the criteria needs to be the same order. So in our, this data set published in the article, the first three criteria was higher the better, and then 4 was the lower the better. So need to keep the same order so that they are monotonically increasing or decreasing. And then using, without writing a code, using this package, we can come up with same ranking. So these are the ideas of my talk, and that's it. Thank you.
Thank you, Dr. Rashid, for your nice talk. So we have some time for discussion. So if any one of you has any question, please, you can ask. You are free to ask. We have some time.
Thank you, Professor Rashid. I am Tawqir Ahmad, Head of Division of Sample Surveys, ISRI. So, thanks for the nice presentation. My query or just clarification from you is regarding the comparison of different methods. Like this Topsys is one of the method based on which you have obtained the result, composite index, etc. We have many more methods, as you very rightly you have shown that there are many methods available, out of which one is AHP, analytical hierarchy process. And in AHP, see, the weights are based on subject matter experts, weights criteria. And after that also there are development in that AHP also, say objective analytic hierarchy process, say these weights are obtained based on the statistical methods or so. We did at ISRI long back. So what I want to know that whether you have done any comparison of your this Topsys method with other methods and how does it perform?
Well, thank you for your question. Actually, I did not. So I did not compare the other method. Professor Sinha and I published a paper where basically we use a different weights. We use the Topsys, but we use the different weights to check the ranking.
Okay, thank you.
Any other question by anyone, please?
Girish, you had question?
Well, see, it's a long list of participants. Nearly 121 participants are there. It's a fantastic gathering. So please feel free to ask any question. And since it is a workshop, I think those who are students, you can also go ahead and ask questions because it's a workshop. So it's a learning platform. So please speak out. And yes, please go ahead.
First of all, congratulations for a very nice talk. I have a very simple questions. When we try to forecast by different estimation technique, suppose different methods we are forecasting, then there are different evaluation criteria, maybe RMSE, MAP, and all kind of things. Then we are going to use TOPSIS to get a ranking of those forecast methods. Is it worth doing it, or like for a given data sets? In univariate time series models I'm talking of, or machine learning, wherever you are, but you have a different estimation technique, different forecasting methods, and then for different evaluation criteria. So you have an alternative on the left, this side, and then you have a different evaluation criteria. Only thing is that you said one of the hypotheses is that all the criteria, like either should be increasing or decreasing, but in your case, some of them were increasing, some of them were decreasing. So is it worth comparing, ranking those criteria? Because I have done in one of the papers, but I'm not very convinced.
Well, thank you for your question. Actually, it also depends on the study or depends on the situations. Yes, some scenarios like, of course, like when you're using the different models for a problem, we estimate the parameters, and then when you have the parameters using that particular model for the same problem, and then you have, for example, standard error and others criteria that you are considering. Of course, based on that, you can rank it. Now, so there are many articles published in that scenario that rank that way. Now, based on the study, that could differ whether it some situation it makes sense, some situation it may not. It depends on the what are the models that fits for that study. Yeah.
Thank you. Thank you very much.
Yeah. Any other question? Dr. Rashid, I have a very, very simple question. So there is a provision, you said that the weights that are given by the subject experts, okay? So my question is, so this is a little bit of subjective. Even there are two persons, subject matter experts, they might end up with different sets of weights. So how robust the method is with respect to the choice of weights, or is there any way to find the choice in some optimal way using something, some criteria? I don't know. So that is precisely I'm just thinking.
Yeah, it basically.
You are muted, Professor. Yeah.
Yeah. Thank you for your question. Yeah, we have seen the scenario as well, like the same data set we have used, and then when you use the different weights for the TOPSIS methods, not probably all the ranking differs. So in some situation, like you might get, say, number one ranking for most of the cases which are relevant to use that weights for this study. And then some scenarios like the weights are not relevant at all, then ranking differs drastically. So I feel like it should be relevant to the study to use these weights. Like in this study, like the one I shared with you, so there are some of the weights, you might notice that some of the criteria is like, it's probably 0.00 something, which is doesn't make any sense to include those criteria in ranking. So in this scenario, basically we need to remove this criteria before we do that ranking. So yeah.
Okay. Thank you. Any other question? Professor Sinha, do you have any question?
I think you're muted.
Because you are
there-
muted. Because you are muted.
There is a question in the chat box. The question is Amritangship by Amritangship Priti. So what was the motive behind selecting only entropy weight?
Well, good questions. So basically my purpose was, or for this talk is to basically the idea represented in this published article. So that's why I was stick with the entropy method. Well, the main idea behind to choose entropy weight, I mentioned earlier that in some situation we need expert knowledge to provide the weight for each of these criteria. Not all the time we have the access to get that expert knowledge, or it is not possible to incorporate that idea corresponding to this criteria. So the good thing about entropy weight is it's a data driven. Okay, so it solely rely on the data. So data will tell the story. So based on the data, we use the entropy method, or we calculate the entropy method. So that was
in continuation to the same question, she's asking, did you compare others as well?
For this talk, I did not, but for other article, Professor Sinha and I published an article. We compare some other weights in that paper.
Okay, thank you. Yeah, Professor Sinha, probably if you have any question, at the time you are muted, so so please.
No, yeah, I don't have any question, but I can add a comment that normally what happens is, as one of the persons who rightly pointed out regarding the weight. So what happens is, we have made a study, or rather than using the entropy weight, we have used the coefficient of variation. For every column, giving the variation in the outcome of different locations in respect of a given criterion, we work out the coefficient of variation, and we use the coefficient of variation to come up with the relative importance weights of different criteria. That is what we did. That gave nice results. And then there is a study of robustness. Somebody pointed out, yes, there is a study of robustness. But as you know, to study robustness, we need big amount of data and spanning over a number of occasions or number of periods. So there was a study where 20 years data were collected, and then one particular method was used, and then the robustness of the method was studied by looking at how the ranking is changing. You don't expect the ranking to drastically change in the next or in the preceding cases. After some time, after a considerable amount of time, it might change. So there are good studies to examine the robustness of any given method of finding the weights.
Okay, thank you for your nice comment, very relevant comment in this context. Any other question?
Sir, good morning. I am Dr. Hassan Islam from the Division of
Yes,
Computer.
please go ahead.
Sir, it was a very nice presentation, and Topsis method was really enlightened us. And I am just aligning it with the application in agriculture. For example, for a farmer, there can be multiple criterias for a crop he looks to grow. Actually, there can be multiple options for him. One can be which crop he should grow that can give him the maximum profit, and what is the yield, what is the requirement, which is the market. There can be the farmer's perspective, and other perspective can be from the government side, Okay, government can also ask farmers which crop he should choose. So one thing can be which can have which is the need of the hour for the country. The second can be which can have the mix good export and so for government there can be different perspective, and for a farmer there can be different perspectives. So there can be different criterias and weightage as well. So can there be a comparative study of different outlooks from a farmer's perspective and from a government perspective or other countries' perspective? So can be TOPSIS can be applied for this sort of comparison. So thank you very much. This was my question.
Professor Sinha, any thought on that?
No, I understand what you said, Dr. Islam. Yeah. So what is happening is definitely the two perspectives could be different, but once you apply the method, all we are doing is we are trying to look to different sources, data sources, and trying to rank them. Even though the two criteria are different, still the results might be the same, or at least there may not be too much of a variation in the ranking. Now, if I say this holds rank number 1 under this criterion, and you decide on the analysis and then come up with an entirely different criterion, then there is a question whether the two are talking about the same thing or not. It could be the interests are different, that's why this is happening. So then the two parties, they should sit together and then try to understand what is going on and come up with a solution. Simply mathematics will not do.
Right. Thank you, sir. Thank you.
Yeah, or I think as Professor Sinha said, these two groups can sit down together and identify the common criteria, and based on this common criteria, they could rank it. Yeah.
Yeah. Any other question by? Yeah, so so there is, it seems there is no other question, and is there nothing in the chat box? So I just want to make one comment, because the two aspects of your talk I really liked, I really appreciate, because one is when you showed the codes, so that gives the confidence in the younger generation that they are using R. Many younger people, I'm sure in the audience, they are proficient in R. So whatever you are saying, that can be done using simple R code. So, and you have also R package. So that's really gives us confidence in applying this method. And another thing is that, which I really like, is that you have shown you have given the example in the context of genetics area, DNA or whatever, in some sense. And I believe nowadays probably any research with any organism generates huge amount of data, and that boils down, brings back everything to the genetics. And in this context, this data integration, actually, this was our earlier understanding when we planned to organize this workshop. So thank you, Dr. Rashid, to bring these two very important issues in your talk. And I believe it's a very, very enriched talk for the younger generation and also for the senior scientists, from both theoretical as well as from application point of view. Anyway, I don't know if we come up with another workshop, we hope to have you again as a speaker. So thank you so much. Thank you again. Yeah. So let's give a big hand.
Let's give a long
hand. Yeah. Thank you. So it's now 9:50. Yeah, Dr. Rashid, you want to say something? Please go ahead.
I said, thank you so much for the opportunity, and look forward to working with you in the future. Mm-hmm.
Yeah, my pleasure. Thank you so much.
Thank you, Professor Mamnoor, from my SRI side.
So now it's 9:51. I think the next talk will start at 10:15. But please be online. If George somehow joins, we can immediately call him. So let's wait for a few minutes. Then the next talk will start at 10:15. 25 minutes later. But since this is another disadvantage of online talk, we can bring
My
the
request
speaker
is that
immediately.
my request to all is let be online, but we can attend to other works in the meantime. But 10:10 sharp, again, let us
Yeah.
be tuned to
Right.
the online
Absolutely.
program. Right, Professor Daniel?
Yeah, absolutely fine. So
Therefore,
we'll be here
let's not
sharp
leave
at
the
10.
platform. Let's be on the platform, attend to other works, and then tune to the platform at 10:10.
But in the meantime, if you want to chat with others,
you can.
You can do that because it's a workshop, so there should be some room for interaction. Although online, you're free to do that. Hello, George. How are you? Hello.
Hello.
George, this is
Hey,
Indrail.
good
How are
afternoon.
you?
I'm good here. How are you?
Yeah. Yeah, I'm okay. Sounds good. After a long time, at least I can see you.
Right, right. You see this picture, cathedral learning? Does
Which
it
one?
bring back some of your memory? Are you seeing my slide?
Oh, yeah, yeah.
Okay.
Yeah, I can see your slide, but yeah, not. Is it in slideshow mode? It looks very small
Should I
actually.
switch? Is this one the full screen?
Yeah, yeah. Now it looks good.
So now it's good.
Yeah, yeah, yeah. Now it's good.
Okay, great.
I have just downloaded. I'm actually downloading. It's almost finished your slides. So if there is any issue, I can also share the screen, but not now. You do it by your own, and in case there is an issue, just a backup.
Okay, right, right. I send you it's a PDF version. It's a smaller for email. Yeah.
Yeah, it's downloading. I'm downloading it.
Okay.
So how is the weather in Pittsburgh? Winter has come up or it's still yet to come?
Yeah, it's a typical fall weather. So pretty nice. Yeah, but probably
Oh,
getting
that's
cold
good.
in December. Yeah. How about in India?
India is now pleasant actually. The heat wave is not there anymore. This year we got a good amount of rain. So now it's very pleasant. It's summer is
Okay.
over, winter is yet to come here in between these two, so it's very nice.
Right. I know it's probably similar to I was from Taiwan. So it's
Yeah,
probably
yeah,
similar.
Eleanor is moving, right? She sent an email.
Right. She just left last
Yeah,
month.
so
to Oregon.
Oregon, she's going to Oregon.
Right.
How is Dan? I have contact with email, but just wanted to know.
Yeah, he's doing good. He did an internship for a while, but he really doesn't want to do administration.
Oh no, he's
I mean, 10
more
weeks,
to
right?
research academics. Yeah. Dan Weiss is more to research and academics. He doesn't want to get into administration too much. Yeah.
Right.
That's nice.
Right. You know, the Pete Hugen just wait. I think they just recruited a new chair. Yeah.
What did you say? They just?
The new department chair.
Oh no, I didn't know that. So who is the chair now?
Right. Yeah. So Eleanor wants to become a dean. So even though she also did the interim chair for a while. Yeah.
Okay.
But she didn't want to stay as the department chair.
Okay.
Right.
Professor George,
hello.
Welcome on behalf of Indian Agricultural Statistics Research Institute. I am Rajendra Prasad at ISRI.
Okay, thank you very much. Yeah, for inviting me.
We are grateful for agreeing to be a speaker in this workshop organized by Professor Indranil.
Yeah, it's my pleasure. We just have the daytime saving, so it's 1 hour back. Right now it's almost midnight, so it's 1 hour better.
Yeah, actually, when I calculated the time conversion, I did not realize that that daylight saving will fall between this planning and the actual workshop.
Easy between 2 days.
Yeah. So just I realized that. Thank you so much, George, shifting your top by 1 hour. Thank you so much. Yeah. Otherwise, yeah. I just realized yesterday night actually. But anyway.
Professor Indranil, I think you can introduce and then we can start.
I think it's only 105. Let's wait for 2-3 minutes and we can start exactly because if somebody joins, so just 2 minutes maybe.
Right. So our time difference is like 13.5 hours. So how does that 0.5 hour, where does it come from?
What is a half hour? I think it's how long is the time? 11 hours, 30 minutes, I believe, right?
Right. So in general, so that's the specific time zone for your location.
Yeah.
Any reason for half hour?
I don't know.
No. Okay. Never mind. I was just surprised. It's the first time I ever seen.
When the subsides the pata kitna आता लो इस तरह मार का पास हाँ अभी पैसे चारों करने
Yeah, I think we can start. Let me introduce Professor George Singh. So it is really our pleasure and it's an honor for me, for us, all of us, to have a scientist like Professor George Singh as a speaker of this workshop. So he is currently the professor of Biostatistics Department, Human Genetics Department, and also Computational and System Biology in University of Pittsburgh. He is the Vice Chair of Research in Biostatistics Department. As we all know, he's a brilliant scholar, got his DSc in Biostatistics from Harvard University under supervision of Professor Wong. He joined University of Pittsburgh in 2003, and he's a leader in the research group of bioinformatics, biostatistics, statistical learning, everything that you can think of in this domain. And he is a prolific scholar. His group has published more than 90 major papers. These are all methodological papers, and more than 115 collaborative papers. And he has 5 patents, co-invention of 5 patents. Recipient of multiple awards, including ASF Fellow, Statistician of the Year, Pittsburgh Chapter, and many other accolades and honor under his belt. I really welcome Professor George Singh to share your knowledge and speak something on this data integration issue. Professor Singh, please, you can share your screen and start your talk. Thank you.
Okay. So do you all see my screen now?
Yeah, is it visible?
Okay. All right. Yeah. So it's a great pleasure that I should say good
you
morning.
Have more or less 1 hour time. Okay, you have more or less 1 hour time, and then 10 minutes for questions.
Can you say that again? How long do I have?
More or less 55 minutes to 1 hour time for the talk, and then 5-6 minutes for questions. Okay.
Okay. All right. So I'll finish by 45. Okay. Yeah.
Okay. Then.
All right. Yeah. So as you see that yeah. So I've been in University of Pittsburgh for 20 years. So you see my slide. This is our landmark of our university. So if you come to Pittsburgh, so this is the second highest academic building in the world. The highest is in Moscow, and our campus, this building is the second highest. Okay, so today I'm going to talk about a topic on selective introduction for multi-omics integrative analysis. So this has been my research area, and a lot of interesting problems to work on. So today my lecture is condensed from a short course that we just taught in April. So this is a very big topic that I try to cover. And I know this workshop is about data integration. So I think it's an adequate topic that I try to cover. But I do not have any research or coverage of agricultural science. So I apologize for that. But if you have multi-omics data, then you definitely can use many of the statistical methods that have been developed that I will cover today. Okay, so because it's a very large topic, there are many review papers, and so if you have interest, you can go to the GitHub, and there are the slides are in the GitHub, and also our lectures are in on YouTube. So this is a short course we taught for the American Statistical Association, and within ASA, we have a section on statistics in genomics and genetics. Yeah. So I will be section chair next year, and I volunteer to teach this short course in April. Okay. So this lecture, as you can see, there are 4 components. So I will go through them. The first component, I will give you the overview of what is multi-omics data integration. And then the lecture 1, I will cover a software suite that's developed in my own lab. We call it the meta-omics. And this is basically when you have omics data that you combine like a meta-analysis, then there are a bunch of tools that we have developed. Okay. And then from lecture 2 to lecture 3 and lecture 4, I will introduce some methods that when you combine multi-omics data for unsupervised clustering, so you cluster the patients to find disease subtypes. Or in lecture 3, that is for the multi-omics for dimension reduction. Okay. And for the final part, I will talk about multi-omics for causal mediation and also for single cell data. Okay. So for each part, I will introduce an example method that is, you will at least have a sense of what are the problems, what's the motivation, and what are the problems involved. Okay. So the motivation, we know that, right? So nowadays we have many high throughput omics technologies, right? So you can genotype the patients, you can measure the gene expression, you can measure methylation or the chromatin opening or the proteins or the metabolome, right? So these are all called omics, okay? So if you have 2 or more omics data, then how do you combine them and then to gain new insights or confirm the insights that you could not achieve that using single omics data, okay? So you can see that the problem really depends on what type of omics data you have and what's your biological purpose, okay? So here, just a table of publicly available data sources. And these are just very commonly the cancer, and also there are some, these are mainly for cancer, but there are many publicly available data that for different diseases. Okay. So, okay. So for a given omics data analysis, right? So you have a bunch of statistical analysis that you can implement. So from your experimental design, and then you have a pre-processing, and then you have dimension reduction, the clustering of the patients, machine learning by classification, and the regulatory network analysis, or the gene set enrichment analysis. Usually people also call it pathway analysis, right? Or association analysis, okay? Or usually people also call it differential analysis, okay? So for all these analysis, you can do it for one omics study, but when you have multi-omics, then you also need to, you can extend your statistical model for each of these basically biological purpose, okay? So for example, yeah, so this is just some, if you look at the DE analysis, you often see this volcano plot, right? So there's a differentially expressed genes, right? Or if you work on the network analysis, then you want to look at the gene modules that are highly co-expressed. Or if you want to do dimension reduction, or like clustering the patients, okay, or machine learning, okay. So let me begin with 2 types of omics integration that usually you will encounter. So for omics data, it's common that you put the genes on the rows, and then you put the patients on the columns, okay? So this is different from our statistical convention, and it's just easier because usually your genes is a lot larger than your sample size. Okay, so you when you have multiple cohorts of data, right? So for example, it could be gene expression, or it could be like a genotyping, GWAS, right? And then you have a multiple cohorts. Then you will align your genes or your SNPs on the rows. And then you have, say, a cohort in India, a cohort in Pittsburgh, another cohort, right, maybe in Japan. Then when you align them, you will see that these data sets are horizontally aligned. So that's why usually people call it a horizontal integration. Okay, so you can see that this type of integration is very similar to meta-analysis, right? For a given gene or a given SNP, then you are looking for some association test or some signal, and then you combine the p-value or effect size across different cohorts, right? So people also could call it a horizontal meta-analysis, okay? So the purpose is to increase statistical power or generate more robust discoveries. Okay, so the second type of omics integration is often called the vertical integration, and it's you have the your patient cohort, and you get their tissue, and then you genotype them, you get the SNPs, and then you can do RNA-seq, get the gene expression, or you measure their microRNA, right, or methylation. So you can see that the patients are aligned on the columns, right? So these data matrices will be aligned as vertical, okay? So the purpose will be different from horizontal, right? Here, you have more complex biology because for a given gene, you have the underlying, say, SNPs regulate the gene expression, or microRNA regulate the gene expression, right? So there will be a more systems biology that's involved, right, when you try to develop your statistical modeling, okay? Okay, so this figure is from a review paper in 2017, I think, the genome biology paper. Okay, so here there's for many methods developed, there are two major categories that they have different concepts. So on the left is called a parallel integration. Okay, so there you treat each of the omics data. You do not put in the say the regulation, right, from RNA to protein, or the copy number variation to messenger RNA. So you do not consider those information in your modeling. So you just treat the data sets as data matrices, okay? And it's parallel. So you basically, if you don't include those information, and the benefit is then whatever method that you develop, it will be easy to generalize, right, to arbitrary number of types of omics data, right? So for example, if you do some dimension reduction, right, so say using NMF, negative matrix factorization, right? So those methods will be very general in terms of the mathematical factorization. So on the right is called a hierarchical integration. So here you try to integrate, so say the CMV or the methylation that regulate your gene expression, and this gene expression mRNA that will regulate the protein expression, right? And then the protein will impact your clinical outcome. So if you try to embed those prior biological knowledge, you can see that the downside is a lot more difficult. Your modeling, your computation will be a lot more difficult. And it will depend on what omics data that you have, right? So if today you have CMV data and mRNA and then protein, right? But then maybe for another lab, they generate methylation and mRNA, right? So then you will need to develop different models to incorporate this biological knowledge, okay? So the downside is it's more not generalizable. You will take more effort to specialize for your data, your project. But then the benefit is it's of course biologically more relevant because you consider those biological prior knowledge. Okay, so these are the two major types when you look at the methods that you have. Okay, I will go over a few methods that the similarity network fusion or drive. That's an interesting, like similar to PCA, but it's an interesting like matrix decomposition. Okay, so those are parallel integration. Okay, and then I will talk about some causal mediation model, and then there you will see that this is a hierarchical integration because you need to consider, right, what's the regulation of the, say, the gene expression and then the SNP, right? So you need to have those prior knowledge to set up your mediation analysis. Okay. All right, so now I need to quickly go through the first part. That's the horizontal omics data integration. Okay. So as I said, this type of problem is more like combining multiple cohorts of the same omics type. So it will be more similar to meta-analysis. Okay, so my lab developed maybe 10 to 15 papers for different purposes. When you want to develop differential expression genes, then we call it a meta-DE, that a package. Then we also have a package when you want to combine multiple study for pathway analysis, right? MetaPath. And then for network analysis, we call it meta-network. And then if you want to do machine learning, we call it meta-predict. And then also cluster analysis, meta-cluster. Okay. So over the years, we develop all the methods and develop those software. And in the end, we put them all together as a software suite. And then we published a few years ago in bioinformatics, and we call it a meta-omics. That's a software paper. Okay, so here I will quickly go through a few methods that we developed, so you have a feeling what it's like. Okay, so for example, if you combine, say, 3 studies, right? So these are the tissue from the brown tissue, from heart tissue, and liver tissue. And then you have the case control, right? Black and orange that you can see here. You have the subject from the black is case, and then is control, and orange is the cases. Okay. So your goal is for each gene by gene, you want to have a powerful statistical test that you can combine, right? Say the p-value from brown tissue and from heart tissue and liver tissue. Okay. So, for example, we published a paper in Annals of Applied Statistics. Then that in 2011, that's a adaptively weighted feature method. So the benefit there is we modify the feature method. In the end, you can decide. So, for example, if you look at the heat map here, I don't know if you can see my mouse. Okay. So the first category of heat map, it would be the upregulated genes, right, from green to red color. And then it's 111. So that means it's a differential expression for brown and from heart and for liver. Okay. So it will be powerful if you combine all 3. But then the method will automatically select. So the second type, this number 59 genes, they are only differentially expressed in heart, right? So you can see there's no signal for brown and liver. So the method can automatically say, I don't combine brown and liver. So the third category, the third gene, these 51 genes would be, you would say, okay, the method will automatically say you combine brown and heart tissues. So you have indicator that you combine 110, okay? So this type of adaptive feature has been popular. We were the earliest to develop, and over the 10 years, there are different versions of adaptive feature methods for meta-analysis. Okay, So it will give you interpretation and also give you power when you combine multiple studies. Okay. Okay. So I will move on. Another method that we call it meta. It's a DCN, so differential co-expression network. So the idea there is very simple. If you have multiple studies, so for example, this the first row, so we have 5 studies, and then for each study you have a ER. I think it's ER positive, and you have 5 studies, and then each study you have the first row is a ER positive, and then the second row is ER negative patients. So our question is, can you find the gene modules? So these dots are the genes. So for example, you are on the left, you have maybe a bunch of genes that are highly co-expressed in ER negative, but then they lose the connection in ER positive, right? And then on the right, these 5 figures, you have these genes that they are highly co-expressed, okay, in all these 5 ER positive studies, right? But then they lose their co-expression in the ER negative, okay? So these are the gene modules that would be very, very interesting because they have differential co-expression. It's the second order of the the differential analysis. Okay, so I will skip the technical detail. Okay, so you know that roughly what you will get from these packages. Okay. Okay, so the third paper that was also a method that we developed, published in JASA. So when you combine multiple studies, then the question would be, I want to find, right? So here, for example, you have these 2 studies, and then you want to find, right, what are the genes on the rows are the genes that you can select that define your clustering, right? And then the second goal is you want to perform clustering, right, for each of the study, right? So these are 3 clusters. And then number 3 is very important. You need to have the patterns that you can match across studies, okay? So basically, this is what we did. We modify a sparse k-means method, and then to achieve all these 3 goals together, okay? So for example, this is I think it's a leukemia study. So we were able to find on the rows, these are the genes that will characterize the patients, right? Study 1, the patients, you have black, red, and green 3 clusters. And then these are the heat map, so the gene expression pattern. And then you can see they have a very concordant gene expression pattern across the 3 studies, okay? So you can, using one target function that you can achieve all 3 goals, okay? So we call it a meta clustering, that you combine 3 studies or multiple studies to do joint clustering. Okay, so here I only give you 3 examples. One method in MetaD and meta network and meta class. So we also have a bunch of methods for combining studies for pathway analysis, machine learning, and PCA. Yeah. So this is a software suite. If you combine multiple studies that want to do joint analysis. So we have a bunch of tools that have been published, and you have the tools to use. Okay. All right. So then I will move on to the second part. This will be the lecture 2. If later you are interested, you can go to the GitHub and you can go to the YouTube videos for detail. So in this second topic, our goal is now it's not a horizontal, now it's vertical. So you have a multiple vertical multi-omics data, and then you want to perform unsupervised clustering on the patients, okay? So biologically, this is an important task because if you have patients that can be clustered, right, by your multi-omics data, then they possibly could represent different disease subtypes, right? Subtype A, B, C, right? And then if they have different disease mechanism, different treatment, right? So you could potentially do precision medicine and then to treat these different subtypes differently. Okay, so biologically, this is a very important task. So in breast cancer, 20 years ago, that the first breast cancer microarray study, so they found the luminal AB and the HER2 and basal. So that was one successful example. In the past 20 years, the breast cancer treatment has gained a lot of advances. So reduce, prolong the patient survival and find targeted treatment. So it's all because, right, these patients can be clustered by the omics data. Okay. So this is a review paper that lists many methods that have been developed for this purpose, combine multiple multi-omics data and then to perform patient clustering. So you can see that some methods will rely on patient modeling, and some are network-based, some are correlation-based, and some are fusion or multivariate-based. Okay, so here I will give you a very quick introduction of a fusion method based method called the SNF. Okay, so the idea is very simple, and you can see that a flavor of what is involved. Okay. Here is another table that involve different methods. When you have different scenario, then what kind of methods that are recommended? Okay, but I won't go into detail. Okay, okay. So this is the general framework. The idea is very simple. So if you have original data, right? So you have multi-omics. So here, say you have two omics data. So one is the gene expression data, right? And then the other is DNA methylation, right? Okay, so you have the patients on the columns that are that are aligned. Okay, so then you can begin with generate a similarity matrix, right? So it could be correlation, it could be some way of the similarity matrix. Okay, so then you have the patients, right? So if you have n patients, then you will be the n by n matrix, right? So you can see that in this example that you can see like you have roughly two blocks, right? Or maybe there's a small two samples, right? That are the clusters of patients. And then for methylation, right, you can also do the n by n similarity matrix. And then if you have a block, that means it's likely a cluster of patients. Okay. So then the key is fusion, right? So they begin with this similarity matrix, and then you can draw the network that you have, right, the visualization. Then the key is they develop certain fusion iterations so that in the end, you fuse the two similarity matrices, right? And then in the end, you can conclude a fused similarity network. And then within this fused network, some of the edges are probably dominated that come from, say, the mRNA base, so that's blue. And some edges are from methylation only, so that's pink. And then if joined, then it's basically supported by both omics data, okay? So you can see that it's basically, when you integrate, you want the homogeneous information to be combined to strengthen the signal. But you want to reserve each data type, they have unique behavior. You want them to be preserved. So you can see that in repeatedly, like I introduced the adaptive feature method, and then now here, when you combine information, you want to combine the homogeneous information, and you want to maintain the heterogeneous, that unique signal from different sources. Okay, so that's basically the essence in many of these multi-omics integration methods. Okay. Later, you will also see in Drive, in other methods, that you have those components. Okay. So basically, I will skip those details. This is more of a computational method rather than a statistical modeling. So they choose a similarity measure and then build a similarity matrix. And then they build an iteration strategy that they have the normalized kernel and then sparse kernel and then have iteration to update until they converge. Okay. So after you have this fused similarity network, then they could build upon it to do disease subtyping, and then they could also do see whether the clusters associate with any outcome. So then they're likely to be useful for the future clinical use. Okay. All right. So this is a figure from their paper. So they combine methylation, mRNA, and microRNA expression. So on the right, it's basically the three clusters they conclude when they combine the three sources of the signal. Okay. And you can see that the survival, the larger dots is means longer survival. So you can see that the third cluster that on the right lower corner, it has the patients usually have a larger survival, longer survival, right? And then the first cluster, they have a shorter survival. The dots are smaller. Okay, so showing that these patients, the cluster of patients, they indeed have a differential survival that clinically could be useful. Okay. Okay, so now I will move on to the third components. And so this topic is about when you combine multi-omics data, how do you perform dimension reduction? Okay, so this direction also has tons of papers that have been published. So I will cover one of the earlier method, and it's pretty useful, and also statistically it's pretty insightful. So the method is called the joint and individual variation explained. Okay, so it's very related to, right, when we do PCA or factor analysis. Okay, so for example, this slide, you begin with, say, you have 4 omics data, right? So the first one is gene expression. Second one is chromosome, right? CMV, so copy number variation. Third one is microRNA, and the fourth is methylation, right? So if you combine these 4 data matrices, right, you can do a very simple stacked PCA, right? So basically you just stack them together, become one big matrix. Then you will have, right, the factorization, right, the PCA. So basically the A1, A2, A3, A4, the columns will be the meta genes, right? And then you have this factor F, right? So the rows in F would be the K factors, right? K is sort of the dimension reduction, right? So this can be done easily, just a traditional PCA by stacking all the data matrices. Okay, so the downside is if you do this, then you don't, as I said, when you combine different sources of data, you want to be able to like integrate the homogeneous information. So you have the joint signal, right? That's strengthened. But then you want to keep each omics data or each source, they might have their individual structure, right? So their unique structure that you want to keep, right? So if you do this very naive stacked PCA, then you don't have the joint and individual, right, structure. You only have the joint. So it won't be a good data integration. Okay. So the idea for Drive, yeah, there's a paper they published in Annals of Applied Statistics. So the idea is pretty simple. So you believe that your k equals 4 in our example. So you have 4 ohmic data, right? So you believe that you can do a factorization, and then each data matrix, it will be the sum of a joint structure, and then A would be the individual, okay, variation, okay. So how do we achieve that, right? So this is just a visually. You want each x, so this x1, x2, right? It has the joint structure, and also you have the individual structure, and then plus some random noise, okay? So you want to achieve that. So in the end, this is how they try to do. So you have x1 to xk, and then every of that would be the sum of 2 components. The first component is the joint structure. So then you have the common U across each of the k, right? Then you have the loading of W1 to WK, right? But then they have the same U, that's the space, the factor. Okay, so U would be the joint, would be the common factors for each of the K matrices. But then you have the individual. So U1 to UK would be their individual factors that can capture the remaining strong signal. Okay, so in the end, you have U, that would be the common factors. And then U1 to UK would be the individual factors that captured by each of the data set. Okay, so basically that's the setup, but then the question is you need to be careful with identifiability and also the algorithm that's can derive the U and U1 to UK. Okay. So this drive is a pretty good method in terms of different purposes. After this dimension reduction, then you can use the factors to cluster the samples, or you can use the factors to predict clinical outcome or associate factors with different clinical variables. Okay, so there was this comparative paper by Cantini. So they compare many methods, and one of them is drive. So in that comparison, if you are interested, you can go to GitHub and look. We have code. So by the way, for each component, if you are interested, you can go to our lecture notes. We have the video and lecture notes. But more importantly, we had this short course with hands-on. So we have all the example data and code. So you can just run through the package and run through the example by yourself easily, okay? So with that experience, we hope that when you have a real project, you know where to begin, okay? So that short course, we spend a lot of time, and I really feel that those hands-on code are very helpful if you are in this area and want to try it. Okay. So now back to Drive. This review paper compare many methods. They use a TCGA, that's the cancer data, compare different, right. So in the end, basically, I will jump to conclusion. So here there are 8 methods, right, on the columns, okay. So then on the y-axis would be basically the performance of the clustering performance, okay, to the underlying clinical subtypes, okay. So you can drive is on the top is the best, and on the bottom it's not the best, but it's pretty good, okay. So just to demo their comparison and performance, okay. All right, so then I will move on to this next topic is a causal mediation analysis. Okay, so the causal mediation, so briefly, you have the exposure, right? And then you have the outcome. So if you have exposure and outcome, you find association, right? So for mediation analysis, you are just asking if you have a mediator, so how much of this association is causally that going through that mediator. Okay, if you fit a bunch of theoretical mediation assumptions, then you can prove that it's causal, right? Okay, so that's the purpose. Okay, so in omics applications, we list a bunch of applications that have been done. So for example, if you use environmental exposure, and then you are asking whether DNA methylation could be the mediator, right, for environmental exposure to associate with outcome, right? And then if you have microRNA associated with outcome, could gene expression could be the mediator that's in the middle, right? Okay, so so I have this slide just briefly. If you never learn causal mediation analysis, so you have Y is the outcome, X is exposure, and then you know X, Y are correlated, right? If do regression is significant, and then you are asking whether the mediator M could be in between that mediates X and Y. Okay, so a common test that is called the product method, that is you do two regression, and when you combine them, then you can try to test. Okay, so the standard way is you model the Y regress on X. Okay, and the C is just those clinical covariates. Okay, then you model Y the outcome on both X and M. Okay, so if you have these first two models, you can plug the first model to the second model. Then you can just quickly you will find that your Y will become, right, X, and then the coefficient of X would be theta plus alpha X times beta M. Okay, so that would be the total effect, right, for this your association. But then this total effect will be able to decompose to the direct effect, that's theta, and indirect effect is the alpha X times beta, right? Then you can test for this the alpha times beta whether they are zero or not. Okay, so this is when your mediator is univariate, right? So this is old, it's very easy to do, and it's very standard. So the question is, if you have very high dimensional on your mediator, right, then there have been a few methods that proposed. So here we quickly mention HEMA method that I will have a slide to show the method. My lab, we just finished a paper that we feel is a lot more powerful statistically than these methods. But here, let's just go over this simple HEMA. So HEMA is published in 2016 in bioinformatics. So what they do is just like what we said. Now, instead of one mediator, now you have P mediator. And then just like Lasso, right, you have only maybe D is small, maybe 5 or 10 out of thousands of mediators, right? That's other effective. So basically in HEMA, they do things pretty standard. So number one, they do short screening, basically marginally do the association, and then just throw away that those mediators that are likely irrelevant. Then they do a penalized regression, and they use a minimax MCP, concave penalty. So compared to Lasso, this will give you more unbiased estimator. Okay. So the final step, the testing, they just use the maximum of the two p-value. Okay. You remember your mediation effect is the product of the two, right? So if one of them is zero, then it's zero. So that's why they use the maximum of the two, so that you guarantee that both of them will be significant, right? That both of them will be non-zero. Then the product will be non-zero. Okay. So this is what they do, and it's actually, if you think about it, it's pretty straightforward, and but it's useful and easy to understand. So they show in the TCGA brain tumor example, and then show that the chemotherapy is associated with 1 year survival, and it's mediated through a bunch of genes. Okay, so these are the at least four genes that have been detected that are the significant mediators between chemotherapy to the 1 year survival. Okay. All right, so I will next to the final topic. When you combine multi-omics data, and nowadays single cell has become a hot topic, and basically technology is amazing, and then you can answer a lot of detailed biological questions. Okay, so I will present a method called the weighted nearest neighbor. It's also pretty simple computational, but then you get a flavor of how it's done. Okay, so the idea from bulk to single cell is pretty straightforward, right? Because when you do bulk RNA, it's a combination of mixture of maybe many cell types, right? So for example, if you have 4 cell types as shown here, right? So if you do a DNA analysis in bulk RNA, and then you say that there's a differential expression, right? So if you say the first row, there's increase, but this increase in bulk, it could be increased in all the 4 cell types, right? Or it could be increased only the green, the dendritic cell, but not in the other 3 cell types, right? But you cannot tell if it's a bulk RNA experiment. So, and then if there's no change, you actually don't know if it's no change in all the 4 cell types, or maybe there's an increase in the B cell, right? But then there's a decrease in CD8 T cell, right? And they cancel out, right? If one increase, one decrease, and they happen to cancel out, then you will conclude no change, right? So the single cell will give you a higher resolution for each cell type, right? Then you can draw a better conclusion. So this is a nice slide I borrowed from someone. I really like it. So it's like, if you do bulk RNA-seq, it's like you have different fruits and you already blended, and then you only get the juice, and then you measure, right, what happens to the juice. But then if single cell, you are still maintaining each of the cell type and try to do inference, and then you understand. For example, if your HIV cell in blood is very low, right? So unless you do single cell, otherwise you never can tell the HIV cell, the differential expression or the characteristic. Okay, so okay, there this is a review paper that there are so many. Yeah, so basically the field has invested so much money and effort. There are many single cell experiments that can be done. If it's a if it's single cell RNA-seq, or if you're unique, it's a one type of single cell, it's now much easier to do. But if you want to do single cell, but you want to do like 2 or even 3 multi-omics at the same time, then it's expensive and not that easy to do. So here is a table that, for example, site-seq, you can measure gene expression, and then maybe hundreds of proteins that use antibody to capture. So this will be a multi-omics with gene expression and protein. And then, for example, 10x, right, that genomics, they can do the chromatin accessibility and nuclear RNA-seq together, okay, for single cell. So they are pretty cool experiments. So, for example, the site-seq, I will go over a paper they target on this data set. So you can measure for a given patient, then you have hundreds of the single cell, and then you can measure their gene expression data, and then you can measure at the same time their protein expression for 163 antibodies. So that means 163, they can capture the proteins, okay? So here, okay, this is another table that shows like many methods that have been developed for different types of multi-omics single-cell data. But this paper in Cell, they developed a simple nearest neighbor multiplication. So it's called the weighted nearest neighbor. So the idea is very simple, but I think I will go over, then you will see what's the motivation and why this is useful. So the idea is when you have single cell data, usually you do a UMAP dimension reduction, then you can see the cells, right, in the cloud, and then you see the data. And then in this data set, they already have the single cell data that's already labeled with the different cell types, so with color, okay? So you already know the labeling, okay? So it's kind of, you know the underlying truth. But now you want to test which method can do well. If you use the single cell data to do clustering, can you recover the single cell types well, right? Okay, so you can do clustering just based on the single cell RNA-seq, right? Or you can do clustering just based on the 163 proteins, right? So that's in the bottom. It's called ADT data. So the idea is, can you combine RNA-seq and protein and then do better, right? So it turns out it's very interesting. That's why this paper go to Cell. It turns out that for some cell types, that the RNA can measure better. So for example, this is an example that CDC, this cell type, if you use RNA single cell, that we will measure much better. And then if you use protein, that will be very noisy, okay? And then if you use the WNN, you kind of use a weighted the nearest neighbor to combine the two. Then the algorithm will determine the weight. It would just help you determine RNA-seq does better, and then you put more weight on an RNA-seq, and then you get the clustering well for CDC. Okay, and then there are other cell types that's reversed. The protein will do better. So this is an example that protein surprisingly will do much better, and then RNA-seq actually will be very noisy. So again, this weighted nearest neighbor, it's a very simple weighted nearest neighbor, but then they have an algorithm to determine the weight that will select more weight for the protein. Okay. And then you can also do good clustering for this CD8 T cell. Okay, so you can see that it's the advantage of the weighting that to decide which to choose to put more weight, and then you can do clustering, and then so that you can do good clustering for all different cell types. Okay. So this is I think it's my final slide. I will pose for questions. So this final slide, you will see that the y-axis is the weight, okay, and for all these cells, right? So you can see that there are some cells. So I think we say case 1, right? So case 1 is the DC. So that would be you put high weight for RNA, right? And then the protein is not helpful for identify this cell type, the clustering. And then case 2 would be the cell type that you often need to put a higher weight for protein so that you can get a better clustering for this cell type. Okay, so yeah, I will stop here. I want to repeat again, for a lot of integration problem, the lesson that we learned is how to, so for example, in traditional meta-analysis, you basically put all the effort to combine the signal. You hope to increase statistical power, right? But in a lot of real data, a complex integration, you have signals that are common. When you combine, you will boost the power. But you have a lot of signals that are heterogeneous. So your method really have to be able to combine signal when they are homogeneous, and then also leave the unique signal out when they are heterogeneous. Okay, that's what we learned for all different types of purpose in the integration. It's a central concept that we have been learning. Okay, So I will, I think, yeah. So, and then there are references. So I will stop here for today. And I really appreciate for your attention. Thank you.
Yeah, thank you, George, for a very nice overview of this data integration paradigm. I would like to invite any participant, if you have any question, please feel free to ask. We have some time.
Sir,
Yeah.
excuse me, sir.
Please
Yes.
introduce yourself and then ask your question.
Yes, sir. Excuse me, sir. I am Mamta Vyas, PhD bioinformatics student. Actually, I'm also working on multiomics data integration only in my PhD research. And I have two doubts, sir. First one is, you have told us about the hierarchical integration. In the hierarchical integration, you have mentioned about the meta network. In that meta network package, it is written that only multiple transcriptomic data we can use. Means, can we use multiomics data? Means in meta network.
Oh, yeah. That package we develop only for the horizontal integration.
Okay, sir.
Right. Yeah, so the purpose is still more to increase the statistical power. Yeah, there are other methods, network-based methods for multiomics.
Sir, actually in a horizontal integration, I didn't get this how transcriptomics and proteomics data we are integrating. Means in parallel integration, I got it from SNF and GIVA, how we are integrating. But in first part, yeah, you have told us about the horizontal integration. In horizontal integration, we integrate the CNV methylation data, and again we are taking the transcriptomic data and proteomic data, and we will get the clinical outcome. And for this, in that metaomics, you have talked about the metaomics paper, and in that some meta network and meta cluster, these packages were there, and these packages only were working on the means, for example, meta network is working on transcriptomic data, and how it is integrating with the proteomics.
Right. I think your problem does not fit for the first part of the metaomics.
Okay.
Right. Yeah. So what I heard is you are combining like CMV, gene expression, this multiomics, right, for this one cohort. So that should be a vertical integration problem.
Okay.
Yeah. And so you need to first identify what is the biological purpose that you are integrating them. Right.
Okay,
so in my talk, I presented dimension reduction or clustering patients. There are also other types. For example, IBAG is another, basically in the end, you combine multiomics to see the association, how to predict the outcome.
Yes, sir.
So you need to first identify your biological goal. And then if you are interested, you can go to some of the review paper. There are some very nice review papers that then you can go in to see what are the methods available.
Yes, sir. Sir, I have another one doubt. And sir, in JIV, we are integrating the multiomics data, and the outcome will be that factor with the samples matrix, which is in rows, it is giving the factors, and in columns, it is providing a samples. I want to know, I want to know what these factors are meant for, means what they are saying, like how to interpret that for further analysis.
That's a very good question. And that's probably the biggest weakness in Jive, that indeed it's like just like all PCA or all projection methods. In the end, that the loading, right, it combines, it's a linear combination of many genes, right? So in Jive, I think the more advanced method later they have also regularization and allow the gene selection. So you should use those versions, and then when you do those factor analysis, you also select the genes at the same time, so that you can avoid you have a drive result that involve thousands of genes. Right.
Sir, gene selection we'll use, and then can we use that for some studies, like not only for subtyping, some, for example, for network analysis, yeah, something like correlation, some other studies? Means actually majority of the omics integration part I am seeing like only for subtyping. Majority of the things are for subtyping only, and this omics integrative studies we can study for other things also. But when we get this only clusters and these factors, actually I saw these factors, I didn't get this what these factors are meant for. Means like they're saying this factors and sample matrix, and while giving the input and while this is processing, it is taking gene expression data, protein expression data, and DNA methylation data. When it is converting and giving it, it is providing the factors. I don't get this, what these factors are exactly meant to be.
No, the factors is just like PCA, it's just dimension reduction. So after the dimension reduction in drive setting is you use dimension reduction, and then after that you use those factors and loadings to do the next step analysis, right? So, but it's just one way of it. So for example, if you do drive and then take the result to do just simple k-means, so that's just one way of doing multi-omics clustering. But you see that there are other methods that's more straightforward. You directly use the raw data without dimension reduction, but you directly model for the clustering. Right. Yeah. So it's there are comparative studies, but it's not necessarily which approach will perform better. It depends. Right.
Thank you, sir.
But for either method, you need to be careful to have the gene selection and then have the interpretation.
Thank you, sir.
Any other question?
Yes, sir. I'm Vaishnavi from Osmania University, Hyderabad, India. Sir, I would like to ask you that while we train the data, how can we decide the hyperparameters like minimum cluster size or number of clusters? As I can see, you have used clustering and k-nearest neighbors in your study. So is there any particular technique that you have used?
Oh, can you repeat again? What's the question?
So I want to know what hyperparameters technique you have used. Like, how did you find there are only 3 clusters in your study, or like that, or minimum number of elements that should be there in the cluster?
Oh, okay. Yeah, so that's a good question. And so the recent advances, okay, so Tipsharani had a few methods that gap statistics, prediction strengths, and then recently we published a paper. We use resampling method that can estimate the number of clusters better. Yeah. So if you are interested, you can email me. I can. We publish in biometrics. So there, our focus is you estimate the number of clusters, and then also you decide how many genes that you use. And it's a pretty general framework for both purposes.
Yes, sir. Thank you.
Okay. Yeah.
Any other question? If you have any doubts, any clarification, this is a golden opportunity to have direct interaction with George. So please feel free to ask anything.
yeah, email is easy.
Yeah, otherwise you can send email. I think that will be fine. Yeah, I think George, we can, it's fine because it's already midnight in your place. Thank you so much for this exciting talk. And I believe you have given a very nice overview of what can be done in this data integration paradigm. There are multiple problems. And I still believe that although you did not use any example or anything from agriculture science, but most of the methods, probably all the methods have direct bearing with agriculture science, because when it comes down to the genetics in agriculture, also there are multi-omics. So I believe all the methods probably can be applied directly. Maybe a little bit of modification might be required. But it's a really very enriching talk, and we all learned from your wise wisdom and knowledge, and it was really fantastic. And thank you so much again. Let's give a big hand to George.
Okay, thank you very much.
Thank you.
Thank you, George. It had been really a wonderful talk, and this has been a very good academic recipe you have given at time of your midnight.
And also he has given the link of all these GitHub materials. There are 4 lectures and materials are there, codes are there. So it's very, very useful, I believe.
Okay. Yeah. You can forward my today's slides. I send you the PDF. Yeah. So these are all safe to, if you want to.
Yeah, I will do that. I will definitely do that. Sure. Yeah.
Thank you.
Okay.
Again.
Thank you so much. Thank you.
Okay. Bye-bye.
Bye. So I think it's 11:20. Let's take maybe 10 minutes break, and we can start our next talk at 11:30. Is that fine?
That will be fine. That should be fine.
So we will again join. We will join after 5 minutes, and maybe we can start a little early if everyone is present. Okay. Thank you. Hello, Professor Prashad. Can we start?
Yeah, Professor Ranil, I think we can start. And
Yeah.
we can invite Professor Gaurang.
Yeah, I think Professor Gaurang Chattopadhyay is there online, so
Yeah.
we can start. So it's my real pleasure to invite Professor Gaurang Chattopadhyay. Actually, we have very long association, probably almost 30 years. So he's my very beloved kind of dada. So it's really a pleasure to have you with us, and you kindly agreed to give a talk. So Professor Gaurang Chattopadhyay is currently the head of the Department of Statistics, Calcutta University. He actually joined this University of Calcutta almost immediately after he received his PhD degree. He worked in PhD thesis during PhD. He worked on the foundations of statistical inference under another great professor, Professor S.K. Chatterjee. Professor Chattopadhyay is a professor of the department since 2012 and is the coordinating editor of Calcutta Statistical Association Bulletin, which is one of the oldest journals actually since 2013. He is a coordinating editor, and he was also the secretary in this journal during 2007 to 2010. She has done excellent research in mostly statistical inference, both parametric and non-parametric, and his research interest is in multiple testing, published many papers in international journals. But his main quality, one of the most important quality that he has, he is not only a good teacher, he is an excellent teacher. And he taught, his teaching versatility is amazing. He has taught many courses like real analysis, complex analysis, Bayes theory, probability, large sample theory, multivariate statistics. Probably you name any topic, he has taught that topic at some point of time. Even sample surveys he has taught. So we are all, and right now he is very busy in, which is very important in Indian context, has been actively involved in popularizing statistics and delivered many popular level talks in colleges, universities, and various workshops on interdisciplinary research. So it's again my pleasure. So you all are waiting to have a very excellent glimpse of your pedagogy. So Professor Chattopadhyay, please, you start your talk, you share your screen, and the floor is yours. Thank you. I'm just giving him a call. I don't know. Oh yeah, he's yeah. Gaurang, we can see.
Is it?
Yeah. Everything is fine.
Is it visible?
Yes.
Okay.
Yes. You have more or less around 50 minutes, and then we can have few questions.
50 minutes.
Around approximately.
Okay. So, thank you, Professor Mukhopadhyay, for your kind introduction. And thank you, Professor Mukhopadhyay, Professor Rajendra Prasad, and Professor Vikas Sinha for inviting me. The topic is an introduction to multiple testing. So this is an elementary introduction. So I start from the very beginning and start with single hypothesis testing. So this is multiple testing. So multiple hypothesis testing. So start with single hypothesis testing. So we have two hypotheses, null and alternative. And there is a test statistic. And we have a rejection region.
So if test statistic is T and it is a right tail test, T greater than or equal to something. If this left tail test, T less than or equal to something. And we know the type 1 error, that is reject H0 when H0 is true. So this rejection is a false rejection. Similarly, type 2 error, do not reject H0 when H1 is true. So usual practice is control this probability type 1 error at some level, so called level of significance, and select a test whose probability of type 2 error is as minimum as possible. Another approach is p-value approach, where if your p-value is less than or equal to alpha, we reject H0, and otherwise we do not reject H0. Now this concept of p-value is very important in everywhere, also in multiple testing. Now what is p-value? Let's start the simple example. It's a simple test statistic T. And we mentioned that, well, this large value of T are contradictory to H0. So this is a right tail test. So reject H0 if and only if this T is greater than or equal to C. So the p-value is probability T is greater than or equal to the observed T under null hypothesis. So what is p-value? So p-value is probability of results like those actually observed. So observed T, or more extreme than those observed. So you see, so p-value, if it is low enough, so we conclude that the null hypothesis is unlikely to be true. So reject H0 if p-value is less than or equal to, say, 0.05, we consider alpha as 0.05, and do not reject H0 otherwise. And we call this test as significant if p is less than or equal to 0.05. And we call effect is significant. So this is so 0 to 1. So p-value is less than, so the black line here, we reject H. So how can we compare this to idea that T less than equal to something or greater than equal to something, we reject H0, and this p-value approach? So you see the critical region or rejection region is like this. So if T greater than T alpha, we reject H0 at level alpha or size alpha. T greater than equal to T alpha is alpha. So this region, the area is alpha. Now you see, if the observed value of T is here, then it is greater than T alpha. So we reject H0. Okay. Now what is the p-value here? So p-value is probability T greater than equal to T observed under H0. So this area obviously is less than the area this. That is probability T greater than equal to T alpha under H0. That is less than alpha. So if T observed is greater than T alpha, we reject H0, and p-value is less than alpha. So these two ideas are identical. Now you consider the T observed is here. So T observed is not greater than equal to T alpha. So we do not reject H0. And what is the p-value? Probability T greater than equal to T observed. And you see, this is definitely greater than this blue area. And obviously, this is greater than alpha. So we do not reject H0. So these two are identical. But if these two are identical, what is the beauty of p-value? consider a simple example, say x1, x2, x3, x5. So 5 observations. And the assumption of the population is normal, with mean theta and sigma square is unknown. And suppose we want to test whether this theta is 0 against theta greater than 0. And the best test is the right tail test based on some statistic t. And suppose your observed t is greater than equal to 2.132, we reject h0, so that the probability that t greater than equal to 2.132 under h0 is 0.05. Okay. So reject h0 if our observed t is greater than equal to 2.132. So this is the cutoff. Now suppose your observed t is 2.14. So what is the decision? The decision 2.14 is greater than 2.132. So we reject h0 and we consider another observed value is 4.5. So traditional approach, the same conclusion, same level of significance in both the cases. Observed t 2.14, observed t 4.5. But you see, in the second case, we are more sure. Why? Now you see. So if observed t is greater 2.14, then your p-value is 0.049. Obviously, this is less than 0.05, so it is rejected. And if the observed value of t is 4.5, then the value is 0.005. So this is also less than 0.05, but here you see the p-value is a measure of the strength of evidence against h. So you can use this p-value is the confidence, of data-dependent confidence. So if you have observed t is more, it's like 4.5, your p-value is this. So you can strongly reject h0 at 0.0. And this is the beauty of this p-value. Now we move to multiple hypotheses. So single hypothesis, so h0 versus h1, multiple hypotheses. So several hypotheses, h01, h02, h0m hypothesis, and we test h01 against h11, h02 against h12, h0m against h1m. Our assumption is the tests for this are available, and obviously p-values are also available. Now, how to tackle so many null hypotheses simultaneously? Now, consider an example. Prostate cancer data. This is a famous example. 52 prostate cancer patients and 50 normal persons. So there are 6033 genes, and data Xij expression level of ith gene for the jth person. So you see ith gene, so I from 1 to 6033, and jth person, total number of persons 50 plus 52 is 102. And the null hypothesis is equality of two population. Is there any difference between these two? So we are testing that, whether there is any difference. And simultaneously for these 6033 genes. So we guess some are few important determinants of prostate cancer. And we want to identify these interesting genes. So this is a part of selective inference. So we have to select a set, and this set of genes associated with this prostate cancer. There are more examples, several examples possible. So you can consider this testing several treatments against a control. We want to know that which of the treatments, multiple endpoints in clinical trials. And I think this is work, the multiple testing approaches for hypothesis in integrative genomics. This is an important research work in 2020, where how to combine data across the various large-scale data types. And it focuses on the use of multiple testing approaches in order to perform integrative analysis. So that is the focus theme of this workshop. So how can we start? So one very interesting way, so union intersection principle by S.N. Roy, considered global null hypothesis, that there are M hypotheses, so intersection of all hypotheses, like so if H is true, the intersection, all of it, and this is called global null hypothesis against this. The rejection region, so if at least one is rejected, then it is rejected. But the problem is, suppose this H is rejected. The question is, what is the reason for rejection? So one cannot further point at the individual hypothesis, which are false. Is it H01 or H05, H19? Okay, so possible strategies. So simplest way is to test H01 versus H11 at level alpha, H02 versus H12 at level alpha, and so on. That is the simplest strategy. And suppose all the null hypotheses are true. But if M is large, the number of null hypotheses, we are certain to reject at least one of this. Why? Let us see the proof. That is very important. So we have to calculate the probability that of at least one false rejection, at least one type. So since all the null hypotheses are true, so any false rejection, any rejection and false rejection are same. So all the null hypotheses are true. So rejection means false rejection. So at least one rejection. So we can write it as 1 minus, so 1 minus probability of no rejection. Probability A complement is 1 minus. Now, no rejection. That is, do not reject H01, simultaneously do not reject H02, and so on. So this and this and this. We assume independence. So this is just product. So do not reject H01 to the power n. Now, what is probability do not reject H01? It's 1 minus. So it is 1 minus alpha to the power m. Now you see, if alpha is 0.05 and m is 21, then this probability is 64%, 0.64. The chance of getting at least one false rejection is very high. And you see, if it is 100, this probability is 0.99. And in this prostate cancer data, that case, number of genes, M is 6033. So the avoid this multiplicity problem, what can we do? So this is a very interesting example. You see, this is the news headline. This green jelly beans linked to acne. So jelly beans cause acne. Investigate 95% confidence, only 5% chance of coincidence. You see, we consider it separately at 5% level. See here, this purple jelly, P greater than 0.05. So do not reject, do not reject, do not reject, do not reject. But probability of at least one rejection is very high, one false rejection. And you see, ultimately here, green jelly beans, P is less than 0.0. So the conclusion is, okay, it is linked to green jelly beans and there is some relation. So that is a problem. So multiplicity, we have to take care of this. Now we define some errors, so probability type 1 error in single hypothesis testing problem. Here, family-wise error rate. And what is that? That I have explained in the last slide, that probability of at least one false rejection. And what is the meaning of family? The family is collection of null hypotheses. So M null hypothesis. So this is the family. And family-wise error rate. So we have considered the whole family and the probability of at least one false rejection. Our aim is to control this family-wise error rate at level alpha. So that is the most important thing. So control this family-wise error rate at level alpha, not individual. This family-wise, we have to control this error rate. Now, how can you control FWER? So fix a set I, the subset of 1 to n. That is, say 1, 2 or 1, 3, 5. And define H naught I as H naught I is true for I belonging to I. Suppose I is 1 and 5. So H naught 1 and H naught 5 are true and others are not true. So several cases are possible. So I, the set of true null hypotheses. And if I is 1 to m, then all the null hypotheses are true. So how to control FWER? One is called weak control. That is, FWER under I, that is I is 1 to m. So all the null hypotheses are true. Then we control FWER. This is called weak control. And another one is strong control. What is that? So FWER I is less than equal to I, whatever. So we are not aware of this I. I is totally unknown. The number of true null hypotheses is totally unknown. So irrespective of, so FWER I is less than or equal to alpha. So control strongly. The simplest and oldest one is Bonferroni procedure. So we have M null hypothesis and obviously alternative hypothesis and p-values, P1 for the first test, so H01 versus H11 and so on, P1, P2, Pm, M p-values are there. And the rule is like this. If this Pi is less than equal to alpha by m, then we reject H0. So reject H01 if P1 is less than or equal to alpha by m, not alpha. When individual case P1 is less than alpha, then we reject. Here, alpha by m. Depends on. Otherwise, do not reject H0. So this is the Bonferroni procedure. But you have to show that it controls this FWPR. That is very important. So I am proving this here, a simple proof. So probability of at least one false rejection. So what is the meaning of that? So I, you see, I is the set of true null hypothesis. So at least one false rejection. False rejection means the hypothesis is the true and you reject that. Null hypothesis is true, you reject that. So Pi is less than or equal to alpha by m for at least one. If I is say 1 and 5, then P1 less than equal to alpha by 5 or P5 is less than equal to alpha by 5. So if m is 5, or m is 10, this alpha by 10 and alpha by. Now you see, this at least one means or, union. So you know this, the probability of union of A, B, C is less than equal to PA plus PB plus PC. So this. An interesting thing is this, under null hypothesis, the distribution of the p-value is uniform 0. So this probability is nothing but alpha by m. So alpha by m into the cardinality of I, the number of times, the number of members in I. And the number of members obviously less than equal to m. So this is less than equal to alpha. And you see, this is less than equal to alpha irrespective of I. So this Bonferroni procedure strongly controls this FWPR. So this is the simplest one, and the technique is very simple. In place of alpha, you use alpha by m. Okay. But where is the problem? You see, if alpha is 0.05 and m is 1000, what is alpha by m? Is 0.00005. And it is very difficult find a test where p-value is less than this 0.0005. If it is less than, then it is fine, we reject. But it is very difficult. So what is the next step? So before that, before the next step, I just want to define one important thing, adjusted p-value. We are rejecting this pi less than equal to alpha by m, and if greater than, we do not reject h0. And adjusted p-value is like this. We are considering only alpha, not alpha by m. And another procedure, it may be another value, say alpha star, alpha to the power m, 1 minus alpha to the power, etc., etc. That may be possible. But you see, if we consider the p-value, we find a function of this p-value so that this pi adjusted is less, just check whether this is less than or equal to alpha or. For this problem, how can we check? You see, pi less than equal to alpha by m means m into pi less than equal to alpha. So your adjusted p-value is m into original p. So multiply with m. But one problem is there, if m into p-value is greater than 1, then you have to consider the 1 as your adjusted p-value. So we can write it as minimum of mpi and 1. So adjusted p-values are directly comparable with the significance level alpha. So that is the beauty of this adjusted p-value. And let's consider one simple example. Suppose P1 is 0.01, P2 is 0.015, and P3 is 0.005. So what is the conclusion? So here M3, and you have to mention alpha. Suppose alpha is 0.02. So what is alpha by M? Is 0.0066. Now check, P1 is less than alpha by M. No. P2 is less than alpha by m. No. P3 is less than alpha by m? Yes. So what is the conclusion? Using Bonferroni's procedure, the decision is reject H03 at level obviously 0.0, but do not reject H01 and H02. But if you consider that alpha, the P1 less than alpha as your rejection region, then all the H01, H02, H03, all are rejected. But here you see only H03 is rejected. Now, what is the adjusted p-value? You see, P1 is 0.01, M is 3. So multiply each value, P1, P2, P3 by M. And you see, this is 0.03, 0.045, and 0.015. Now compare with alpha. And what is alpha? 0.02. You check. The decision remains same actually. It should remain. But the interesting thing is, you have to consider only alpha, not alpha by m or something. So this is the benefit of using this. So next one is the sequential procedure. The Bonferroni procedure is a single-step procedure. And this Holmes procedure is like this. Your setup is same. So H01, M null hypothesis, M p values. But you ordered the p values. So P1, P2, Pm are ordered p values. And we write associated null hypothesis as H0 bracket 1, H0 bracket 2, H0 bracket M. And I just explain it. Suppose P5 is the minimum of P1, P2, Pm. That is P order bracket 1. And that is the minimum value. So you see, since P5, it is related to H05. So H05 is nothing but this H0 bracket 1. So first one, H0 bracket 1 is related to P bracket 1. P bracket 1 is nothing but P5. And P5 is related to H05. So H01 is nothing but the hypothesis, fifth null hypothesis, H05. Okay. Now the procedure. This is a step down procedure. So start with P order 1. Now you see, if P order 1 greater than alpha by M, that alpha by M used in Bonferroni's procedure, retain all null hypotheses and stop. You see, all the p-values are greater than P1. P1 is the least one. And this P1 itself greater than alpha by M, so that all the p-values are greater than alpha by M. So we do not reject in each case. Okay? So retain all the null hypotheses and stop. But if this is low, that is P order 1 is less than alpha by M, you reject H01 bracket 1 and continue. Because P order bracket 1 is related to H0 bracket. Okay. Next step is the second largest, second one. So P2. So P bracket 2 is greater than alpha by M minus 1. You see, in the Bonferroni procedure, it is alpha by M for all the p values, but here is alpha by M minus 1. So alpha by M minus 1 is slightly greater than alpha by. So it is we are in some advantageous position than this Bonferroni procedure. Okay. Now here, we do not reject H0 bracket 2 to H0 bracket 2. So this and stop. But if P, this order 2 or bracket 2 is less than equal to alpha by M minus 1, we reject H02 and continue. And this is the way. So alpha by M, then alpha by M minus 1, then alpha by M minus 2, alpha by M minus 3, and so on. What is the last one? If Pm greater than alpha, if it is 3, then divisor is n minus 2. If it is m, it's 1. So m minus m. So Pm greater than alpha. So last one, Pm, P bracket m less than equal to alpha, we reject H not m. And stop, Pm greater than alpha, we do not reject H not m. So you see, the last case, we are comparing with alpha. In Bonferroni problem, we are comparing the alpha by m with all the p-values. Here, this is a sequential procedure, a step down procedure. Okay. But the interesting part is it controls FWR strongly. So obviously, this is a better approach. Okay. Now the problem is, if M is very large, control of the FWR is much too strict. And little chance of detecting at least one false rejection. It tends to reject very few null hypotheses. Very few null hypotheses. So we have to identify. We identify the cases, identify the effects. So it is very difficult to identify. Okay. So alternative suggestion, in place of FWER is another error. It's called KFWER, which is probability at least K false rejections. So K may be 5. So at least 5. So at least one false rejection, very strict. So that probability is high. So consider at least 5 false rejections and control this KFW. So this modified Bonferroni procedure is like that in place of this alpha by m, use K alpha by m. So if it is 5, so 5 alpha by m. So you see, 5 alpha by m is definitely larger than, so there may be more rejections. So this is another procedure, and this procedure controls KFW strong. Okay. The next one, which is very, very important. This is the work Benjamin Hirschberg in 1995 is a path-breaking work. So another error rate. So let us see what is false discovery rate. We have M null hypothesis, H01, H02, H0M, and we have p-values are there, fine. Now what is a discovery? Discovery means reject a null hypothesis. So the effect is significant. So reject a null hypothesis. But what is false? False discovery, reject a true null hypothesis. Discovery, but that is false. It's not one is true, we are rejecting this. Suppose R is total number of rejections and V is total number of false rejections. Okay, so total number of rejections R and total number of false rejections is V. What should be false discovery rate? False discovery. False discovery means V out of the number of discoveries. So the false discovery proportion is V by R. Obviously, if R is positive and if R is 0, we can take this. So this is false discovery proportion, but this is random. This is random. So we take this expectation. This is called false discovery rate. So this false discovery rate. And expected proportion of erroneous rejections among all rejections. All rejections are erroneous rejections, false rejections. That is V. So V by R. I've just mentioned the paper, this JRSS Series B, 1995, Benjamini and Hochberg. Their rejection rule is just opposite to Holmes procedure. Holmes procedure is step down, here it is step up. You see, there we have started with P order 1. Here we start with P order M, the maximum P value. And you see, if the maximum P value is less than equal to alpha, all the remaining P values are also less than equal to alpha. Therefore, we reject all the null hypotheses and stop. But if the maximum P value is greater than alpha, then do not reject H naught and continue. Okay. What is the next one? So in place of alpha, now consider M minus alpha by M. The first one is M alpha by M, that is alpha. So if this, so this is, it should be Pm minus 1. Pm minus 1 is less than equal to M minus 1 alpha by M. Reject H naught 1 to H naught M minus 1 because all the values k from 1 to M minus 1, all are less than equal to M minus 1 alpha by M. So we reject all from H naught order 1 to H naught order M minus 1 and stop. But if it is greater than M minus 1 alpha by M, do not reject H naught M minus 1 and continue. And what is the last but 1? So P order 2 is less than equal to 2 alpha by M. Reject H naught order 1, H naught order 2, bracket 2. There is no ordering in null hypothesis. So, and stop. And if it is greater than 2 alpha by M, do not reject H naught 2 and continue. The simple idea. And last two are like this. If P order 1 less than equal to alpha by M, then reject the first H naught bracket 1 and P1 order 1 is greater than alpha by M. Do not reject this and stop. So this is the simple procedure, but this is a step up procedure. That's opposite to this Holmes procedure. But the beauty is that it controls FDR. It controls FDR. But in the first paper in 1995, we have assumption of some independence of P values. But if you consider several hypotheses, the chance of independence is very rare. So that is a problem. But Benjamini and Yekituni in 2001 analysis of statistics under some dependence, some positive regression dependence of Benjamini has the same procedure controls FDR at level under this dependence. But what about the dependence or independence in FWER control? Bonferroni and Holmes procedure control FWER strongly at level alpha, regardless of the p-values are independent. We have proved that this Bonferroni procedure controls FWER strongly, but we have not assumed that they are independent or something like that. So that is the important property of this Bonferroni and Holmes procedures. Okay. One interesting observation is that FDR is always less than or equal to FWER. So if you control FWER, you can control this false discovery rate at the same level. Okay. So the control of FDR assumes that when many of the tested hypotheses are rejected, it may be preferable to control the proportion of this, rather than the probability of making even one error. And that is your FWER. So it is preferable. But in 2001 analysis of statistics, they have shown this Benjamini-Hirschberg procedures. In place of alpha, I'm writing some Q, so that this FDR less than equal to Q into this, and you take it as alpha, so that what is Q? Alpha by 1 plus half plus 1/3 plus 1 by n. Obviously very small. So that is a way it controls FDR under any sort of dependence among the p-values. Okay. So this is, but you see, it's very conservative. Now consider one illustrative example. Suppose in place of 603, this consider 3, M3 for illustration. So first sample this observation and second sample this observation. We compare. So how can you compare? Which of the 3 genes are differential in space? So we apply two-sided two-sample t-test under the assumption of normality. Otherwise, you can use non-parametric test. But suppose under the assumption of normality, we consider two-sample t-test and find the p-values. And you see, how can you find that? So use t-test and find p-value. So here you this data x1 and y1 for the first one and two-sided alternative. And suppose we assume this t-test, so variances are equal, and find the p-value. So for the first one. Similarly, for gene 2 and gene 3, we can find p2 and p3, and we calculate the adjusted p-value, and this is the result. So you see, adjusted p-value is 1. So we are comparing with alpha, 0.05. This is 0.06. So do not reject. Okay. So you see, here you see, you use Holmes procedure, it is 0.44. So obviously do not reject, but here it is 0.046. So we're comparing with 0.05. So here we reject this. So you use Holmes procedure. Here we use Bonferroni procedure. For this problem, it is not rejected. We can't identify this, but here this is rejected. Because Holmes procedure is more powerful than the Bonferroni procedure and less conservative. So you can use this prostate data and analyze this. So in place of P1, P2, P3, you have P1, P2, P6033, and you can calculate the adjusted p-value and check which one is less than 0.05 and which one is not less than 0.05, so that you can identify the interesting genes. So you see, here this number 48, number 49, they are interesting genes. When we consider this alpha as 0.05, and the standard practice for this multiple testing is taking alpha as 0.1. So here also you see the both Bonferroni and Holmes, they're almost set. Same genes are identified as interesting. And if you use this Benjamini-Hirschberg and this Benjamini-Ekitveli, then also we can use this one. So this Benjamin-Hirschberg identifies these genes as interesting genes, and Benjamin-Ikitili as this. So if we identify this, these genes are maybe responsible. So you can suggest that these genes are possibly interesting genes. So that is a way to identify which hypothesis reject. Okay, these are references. Is a textbook, Lehman and Romano. You know the testing of hypothesis. We have one chapter on multiple hypothesis testing. This is the path-breaking paper, 1995, Benjamin-Hirschberg, JRSS Series B. And there's a book by Brad Efron, Large-Scale Inference. That's an approach of using empirical-based technique, using stories technique. And this is another one, this analysis of statistics, Benjaminian theory. And Professor Shonok Sarkar has several papers on multiple hypothesis testing. It's a very interesting paper in Shankha on methods controlling the false discovery rate. So these are the references. And thank you.
Thank you, Professor Chakravarty. As always, as usual, it's very and nice talk. Actually, everything is crystal clear, at least to me. I don't know. So anyway, it's a brilliant talk, and so we have some time. So if you have any question, please feel free to ask. I see just there are a few questions in the chat box. Himadri Ghosh asked that what is the level of significance of combined hypothesis alpha in Holmes procedure as demonstrated?
No, it is generally conservative. You see, in Holmes procedure, this is the Holmes procedure, and we are considering this FWER, and it is conservative. Obviously, it is less than alpha, but it is always less than alpha. And whatever the beauty is, whatever the true set I is the set of true null hypothesis. And whatever I, this FWER is less than alpha. Generally, all are conservative. So this is exactly alpha. So that is a good question. But for FDR, this false discovery rate, we can show that this is exactly alpha under certain conditions. But here, this FWER is less than alpha because we are in the proof. You see, when we are proving this, so the proof is very important. We are using, so for Bonferroni procedure, we are using the inequality less than equal. So probability A union B union C is less than equal to PA plus PB plus PC. So we are using this Boole's inequality. So this inequality is really strict. So this is very conservative. So definitely, exactly what is the value of this? So if you know the value, then you can control. You can put more, you can increase the rejection region so that it covers this whole
up. Okay, Dr. Ghosh, if it is clear to you, it's fine. Otherwise, you can also ask questions. I'm asking Dr. Himadri Ghosh, is it clear to you, or you can ask questions? Okay, so there is another, I don't know, echo is occurring and not clearly audible. Is it, I don't know whether all of you are facing this problem. Echo is occurring and not clearly audible. I can hear everything.
No, that may be problem. That may be problem at his end.
I think it might be an issue, audio issue in your side. Please check. Yeah, it's audible. Maybe it's fine. Anyway, so the next question is, how do we decide about p-values or adjusted p-values for the, I think, tests with name and structure?
What is?
How do we decide about p-values or adjusted p-values?
No, this
for
is no
name and
structure. So that is a different issue. That is a conditional test, and that is a different issue. So here we are considering this test where p-values are comparing. We are comparing these p-values. Sometimes it is less than alpha by m. Sometimes alpha by m minus 1. You see, for the Holmes procedure, it is more difficult. You see, the Holmes procedure, sometimes it is alpha by m. It is sequential procedure. Sometimes alpha by m, sometimes it's alpha by m minus 1. But if you have the adjusted p-value, just you consider it with alpha. Then you don't have to take care of this, whether this p order 5, it is less than alpha by something. So that is the beauty of p adjusted p. And Lemon structure and similar tests are different things. That is when we are considering the uniformly most powerful unbiased test, and then the Lemon structure.
Yeah, I think this has nothing to do with the typical type of test. All you need to know what is the p-value. Once you get the p-value by whatever,
you can do it by calculating this p-value fine. But if you use R, then they are giving you definitely the adjusted p-value so that you can easily compare with alpha.
So it has nothing to do with the name and structure or any other structure.
No. And then there is a conditionally test. Conditionally.
Yeah. Any other question? Yeah. Another thing is that another request is that can you please share the slides with us?
Sure, no problem. Definitely.
So, I think you can send slides to Professor Prasad and you can distribute it, I think.
Yeah. Yes, sure.
Anyway, this session is being recorded, so I think
it will be available on YouTube with the permission of the eminent speakers.
Sure, no problem. Or if anyone has any question, they can send me email so that I'll discuss it.
Okay.
I'll be glad to answer their questions.
Dr. Himadrigo said that, okay, shall discuss in person.
Sure.
Any other question?
And regarding Professor Himadrigo's question, I just want to mention one thing. Those who are interested in research. So you see, this Benjamini-Hochberg procedure, it controls the FDR, but you see this FDR is exactly equal to the number of true null hypotheses, the cardinality of this I divided by M into alpha. So as I have, you see the proof of this Bonferroni procedure, you see, here you see, this is alpha by n, because under null, this is uniform distribution, uniform 0, 1. So you take this sum. So this is cardinality of I by m into alpha. What is the cardinality of I? The number of true null hypotheses. Suppose it is denoted as m naught. So actually it is m naught into alpha by m. One way, if you know m naught, then we can improve this, can improve the power of this. So big area of research is to estimate this m naught and some adaptive procedure based on this. So you can estimate this m naught, which is definitely unknown. So number of true null hypotheses is definitely unknown. So you estimate this m naught, and on the basis of that, we can improve this FDR, these procedures. So that is another area of research in multiple testing.
Any other question? So I believe there is no other question, but again, so if the participants want to discuss anything, we have few more minutes, so this, you can open up the discussion. Discussion is open, so if any participants wants to make any comment on or anything on the all the three talks amongst ourselves, we can have a chat. It seems okay. Sort of three talks. I think it's also nearly lunchtime. But anyway, thank you so much, Professor Chattopadhyay, for your fantastic talk. And you started from the very basic thing, and finally the approach is very gradual, I should say, and the concept is more or less clear. And one thing I should comment that if we see that the first two talks everywhere during the entire data integration procedure, whether it is horizontal or vertically, any context, whether it is agriculture science or any other science, this p-value always appear, always come. And now with multiple amount of many genes, so multiple testing is an issue. So we have to take care of this p-value correction in order to actually get the kind of associated features, I should say. It is not true that all the associated features will be causal. That will be another area of research and discussion. However, whatever be the situation, this FDR control we have to do this FDR control. There is no other alternative. All questions will come after that, might be regarding the functionality with respect to the actual discipline. So again, thank you. Just give me a second, because there are two comments again in the chat box. One question is that how does Bayesian approach help to decide p-value?
Yes, I have just mentioned that that Brad Efron, this Brad Efron's book, this empirical Bayesian approach. So if you know the probability, so I think you can send email to me and I can discuss this. So that is another one, another approach by Story, Efron. They are considering a slightly different approach and empirical based approach.
So Efron's thing is this log FDR local?
FDR, small f, small f. So they consider some Z in place of this. So Z value and
so thank you, Professor Chattopadhyay, for your again exciting talk. Thank you so much. Let's give him a big hand.
Thank you.
This has been really wonderful. This is such a difficult topic in such a easy language, which can be understood by everyone.
Exactly.
Professor Goren, we are really grateful to you.
Thank you.
And would love to have more lectures from you for our students, because that is going to be really useful to them. Over to Dr. Ajit for formal vote of thanks.
Thank you, sir. So friends, with this we come to the end of a very successful workshop. So we are extremely grateful to Professor Indranil Mukhopadhyay ji, the chairman of this workshop. Thank you, sir, for arranging excellent speakers for this workshop. We are grateful to all the three outstanding speakers for their brilliant presentations. Thank you so much, Professor Mamunar, Professor George, and Professor Gaurangdev for your very enriching talks. We are thankful to our very senior colleagues, specifically Professor Vikas Sinha ji, for sparing his valuable time. Thank you so much, sir. We are thankful to our director, Professor Dr. Ajit Saji, for his encouragement and guidance. Last but not the least, our thanks to all our fellow colleagues and dear students for joining this workshop and fruitful academic discussions. Thank you, one and all.
Thank you. We depart to meet again. We depart to meet again. Ajit, you can close the meeting.
Yes.
Yeah, sure. Okay, bye.
Thank you, sir. Bye-bye.